So there is a natural variability in the landscape associated with the conformational transitions for these three pairs. Okay, so we have published this in the subsequent paper in 2006. So now we wanted, so we answered the first question, is, namely that it's very general. It's not only, p-selectin receptor, but it's also L-selectins, and it can also be other molecular pairs. Doesn't have to be PSGL1. Now we want to understand the molecular origin. Okay, so we cannot use all atom simulations in order to address this question because the molecule, the complex itself is huge. In here we have around 300 amino acid residues, and then in the ligand we have around 20 or 30, and 20 amino acid residues plus 6 sugar bases. So it's a huge system for MD simulations. Okay, so what we did, we used coarse grain models, and in the coarse grain model, basically instead of amino acid residue, we retain only C alpha, okay, and the center of mass of side chain. So this is your C alpha. So each amino acid residue is represented by the C alpha and the side chain, center of residue, center of mass for the side chain. So by these two balls. Okay, one can mimic hydrogen bonds. There's a way, and then one can mimic SS bond, disulfide bonds. There are 4 or 5 disulfide bonds shown in here in red, and one can model these SS bonds as well. And then the potential energy is coming from bond length potential, side chain, side chain backbone connectivity potential. This is this potential. Bond length is this potential between this bow and this bow, vibrations. So basically these are all vibrational energies. Bond angle is this one, bending against this bond. Dihedral angles, these are 5 psi angles, that are very sensitive to the secondary structure of proteins. Then you can also model hydrogen bonds. Then you also have non-covalent interactions because this guy is not covalently bound to this one, but they can come very close to one another. So one has to excluded volume effect, etc. So one has to model this interaction as well, and then SS bonds. So there's nothing new in these. These have been developed by these guys, Ken Dill, Bringenson, Volinus, Karplus. These are the beginners of these methods, and these methods are very old now, 15, 20 years old. When I was applying for a job, people were skeptical, looking, what happens to water, etc. But now everybody accepts the validity of these methods, and these methods, continue to prove their importance in describing huge biomolecules. Okay. So you create a coarse grain model for the protein, for the ligand, then you do it for the receptor. Then the third step is, the next step is, so you do it for the protein, then you for the receptor, then for the oh god, there's an error here. So you do it for the receptor, then for the ligand, and then you have to mimic somehow the binding interface. So this is the binding interface in here. So this is your ligand, and it binds to the surface of the receptor. So receptor surface is shown in blue. This is EGF domain. This is lectin domain of p-selectin receptor. That's human p-selectin receptor. So now the ligand is very difficult to model because it has, like I said before, this protein portion. Then it also has sugar portions. So you have in here sucrose, etc. So this is the sugar portion. Okay, this is not protein but sugar. So it's glycan. So it's glycan portion of the protein. So you see in here that interaction is mostly electrostatic because I have lots of charges on the surface. So now, once I have the potential energy for the receptor, for the ligand, and for the ligand-receptor interaction, then I have total potential, which I have to amend to include the effect of pulling force. So that's F pulling force, and X is the end-to-end distance, and C terminal of receptor and N terminal of the ligand. And then now I have to solve stochastic ordinary differential equation. Okay, that's the first order differential equation with some stochastic term. And stochastic term is basically Gaussian white noise. So that reflects the influence of water molecules. Okay, so I have to have stochastic white noise, otherwise I will not have distributions. In order to have probability, you have to have stochastic term. Okay, So, and this, stochasticity is being modeled by this term, okay, GJT. So, and this one, J is index running for all particles in the system, particles of the receptor and particles for the ligand, okay? And then I have to solve it numerically, repeatedly, in order to obtain the dynamics of unbinding, okay? And so this is the movie of unbinding. So what I do is, just to mimic the AFM experiment, okay, I ramp force from 0 all the way until it breaks. The linear increase rate is this one, 0.028 newtons per second. The total duration of this trajectory is half microsecond. So this is my receptor. This is my ligand. So receptor is shown in blue. The backbone and side chain particles are shown in blue. SS bonds are shown in yellow. You can see in here, there's 1, 2, 3, 4, 5 pairs of 5 SS bonds in here that stabilize the overall structure of the receptor. Now, I fix the N terminus of p-selection, just like in the AFM experiment, because this guy is sitting on the surface, and cantilever tip is going back and forth like this. So now I want to study unbinding, so all I have to do now is to apply pulling force to the C terminus of my ligand in this direction. And like I said before, it has sugar portion, which is shown in red, the ligand, PSGL1. And then it has this, it also has protein portion that is shown in green. So what you can see in here is that now, like I said before, it's a fork with 2 legs. So this one leg, and you can see in here, the one leg unbinds, and then it turns around. Okay, this first was LR1, now this one is LR2. And there is a huge conformational transition, you saw before 5-point-some nanometers, and that actually corresponds to this transition here. It's not exactly along the unbinding trajectory, but it's a rotational motion actually. Okay, now I managed to unbind this guy, and now what I have to do is now to unbind this guy, and it's going to take some time until I stretch, this part of the chain all the way until I start rupturing these contacts. Okay, so why don't we wait till I think I have my time is up. Okay, I didn't notice.